Welcome back to Boring Science. Take a deep breath, get comfortable, and let your thoughts drift among the stars. If you haven't already, gently tap that like button and subscribe to join us on more quiet journeys through the universe. Tonight, we're asking one of the biggest, most mysterious questions of all. Are we alone out there? No hype, no rush, just a slow, thoughtful exploration of life beyond Earth, what science says, and what we're still trying to understand. Let's begin. The question of whether aliens exist is one that has captured the imagination of scientists, philosophers, conspiracy theorists, and late-night radio hosts for centuries. It's one of those questions so deeply tied to our place in the cosmos that it dances uncomfortably on the line between science and existential dread. After all, if we're not alone, what does that mean for us? And if we are alone, what does that mean for us? Either way, it's a lot to process. From a scientific perspective, the question, do aliens exist, isn't just idle speculation or the stuff of sci-fi novels. It's a legitimate inquiry rooted in empirical observation, theoretical models, and a whole lot of statistical probability. Modern astronomy, biology, chemistry, and physics all contribute their own tools and theories to the investigation. And while we haven't yet had the pleasure or horror of sipping coffee with a gray-skinned being from Zeta Reticuli, the evidence and logic suggest that life elsewhere in the universe is not only possible, it may be probable. But let's not get ahead of ourselves. First, we need to define the scope and frame the problem properly, because aliens is a loaded word that often invites images of flying saucers and abductions, not scientific rigor. To start with, let's clarify, when scientists talk about extraterrestrial life, they are usually referring to any form of life not originating on Earth. That can mean bacteria, fungi, photosynthetic slime, or intelligent species capable of interstellar communication and possibly witty banter. But the baseline is life, not little green men. In fact, even finding a single-celled organism on another planet would be one of the most profound scientific discoveries in human history. No ray guns or crop circles required. The importance of this question extends beyond curiosity. It touches on fundamental assumptions we hold about biology, chemistry, planetary science, and even ourselves. The discovery of life elsewhere would indicate that life is not a cosmic fluke, but a natural outcome under certain conditions. It would push our understanding of evolution, adaptation, and survival into new, universal dimensions. It would also prompt a few awkward conversations in theology, philosophy, and politics, because rewriting our place in the universe is never a smooth process. But the question isn't just, do aliens exist? It's layered. Are we talking microbial life or intelligent civilizations? Are we seeking active communication or just passive evidence? Are we asking about the past, the present, or the future? The universe is 13.8 billion years old, and we've only had radios for about a century. The chances of two civilizations overlapping in time, both technologically advanced enough to notice each other and close enough for signals to reach across the cosmic void, are, well, let's just say the odds don't exactly make Vegas tremble. And yet, here we are, listening, searching, calculating. Because even if it's difficult, even if it's unlikely, we can't ignore the question. So where does the scientific process come in? This isn't about wishful thinking or YouTube documentaries with spooky music. The search for extraterrestrial life is guided by observation, hypothesis, data collection, and falsifiability. We look for biosignatures, chemical traces in planetary atmospheres that suggest the presence of life. We aim radio telescopes at the sky to detect structured signals that may indicate intelligence. We examine meteorites for complex organic molecules. We explore hostile environments on Earth, like deep-sea vents and acidic lakes, to understand how life might thrive elsewhere. It's not guesswork. It's a massive, interdisciplinary effort that combines cutting-edge technology with a persistent question that humanity refuses to let go. The motivations for this work are both scientific and philosophical. Understanding whether life exists elsewhere helps us understand how life begins, how it survives, and what its limits are. It helps us contextualize our planet's uniqueness, or lack thereof. It even raises ethical and strategic questions. For example, should we actively broadcast our presence to the universe? Or is that the interstellar equivalent of putting your home address on a bathroom wall? There's also the psychological angle. The question of alien life triggers something ancient and primal in human cognition. We are narrative creatures, always seeking connection, explanation, and pattern. The idea of extraterrestrial life challenges the ultimate anthropocentric narrative that humans are the pinnacle of existence. For some, that idea is exhilarating. For others, it's terrifying. And for a small but vocal group on Reddit, it's proof that the government is hiding things in Area 51. Spoiler, it's mostly classified aircraft testing mostly. Still, the question persists not because it's easy to answer, but because it might not be impossible. We're closer than ever to potentially finding microbial life in our solar system, perhaps on Mars, Europa, or Enceladus. Telescopes like the James Webb Space Telescope are examining the atmospheres of distant exoplanets for signs of water vapor, methane, and other chemical hints that life might be present. We're sending probes deeper into space, building AI to recognize patterns we can't, and engaging with international protocols just in case we one day do make contact. Of course, we must be cautious. Scientific history is filled with premature conclusions, from Martian canals to pulsars initially dubbed LGM, short for little green men. The burden of proof is high. One ambiguous signal or blurry photo doesn't constitute evidence. And yes, most UFOs turn out to be weather balloons, satellites, or, in one tragic case, a seagull caught on a camera lens. But even among the false alarms, the search continues because the stakes are too high and the implications too grand to stop now. In conclusion, the question of whether aliens exist is not just a sci-fi trope. It's one of the most important and challenging scientific inquiries of our time. It forces us to combine hard science with deep philosophy, rigorous skepticism with boundless curiosity. The universe is vast, and we are small, but as far as we know, we're the only species asking the question. That, in itself, might be the most alien thing of all. Before diving into the actual search for extraterrestrial life, we need to ask a more basic question. What exactly are we looking for? What do we mean when we say aliens? The word itself is wonderfully ambiguous, conjuring up everything from tiny green humanoids to floating gas bags on distant worlds, or even hyper-intelligent, disembodied AIs silently mining energy from neutron stars. In scientific terms, though, we must resist the urge to picture creatures with shiny suits and oversized craniums. Instead, we have to define extraterrestrial life based on what we know and allow for a whole lot that we don't. Let's begin with the simplest definition. Extraterrestrial life refers to any living organism that originates outside of Earth. That's it. It doesn't have to be intelligent, curious, or even photogenic. It can be microbial, multicellular, chemical, or, if you're really feeling imaginative, based on something other than DNA. Scientists tend to start with what's called life as we know it. Carbon-based organisms that require water, energy, and a reasonably stable environment. After all, we only have one data point, Earth. and science tends to work best when it doesn't leap too far from data points. That said, speculation is not only permitted, it's encouraged within the bounds of logic and chemistry. For instance, if life on Earth thrives in extreme environments, such as boiling sulfur vents, radioactive waste, or solid ice, why should alien life not do the same? Or even better, why not envision organisms that breathe methane instead of oxygen or metabolize sulfur instead of glucose? These ideas aren't sci-fi fantasies. They're the basis of astrobiology, a field built on understanding both the universality and the flexibility of life. Now let's break things down further. There are typically three major categories of alien life that scientists consider when framing the question. First is microbial life. This is the most likely and least controversial form. If life evolved elsewhere, odds are it started small, like single-celled small. Microbes are resilient, adaptive, and sneaky. They can survive radiation, desiccation, freezing, and boiling. Some can even survive in space for short periods, just to show off. If alien life exists in our solar system, say on Mars, Europa, or Enceladus, it will almost certainly be microbial. And while a Martian amoeba may not win any interstellar beauty contests, its discovery would be revolutionary. It would prove that life is not unique to Earth, and that it may arise whenever and wherever conditions are right. It would also give biologists a collective heart attack from excitement. Second is multicellular or complex life. This includes plants, animals, fungi, or whatever analogs exist out there in the universe. For this kind of life to evolve, a planet likely needs more stable, Earth-like conditions over a long time scale. That means a breathable atmosphere, liquid water, plate tectonics for nutrient cycling, and ideally no apocalyptic asteroid impacts every couple million years. Complex life also implies a certain level of ecological complexity, food chains, reproduction, maybe even social interaction, but probably not spacefaring squirrels. Probably. The leap from microbial to multicellular life on Earth took over 1 billion years, and it might be the bottleneck for alien evolution elsewhere. Third is intelligent life. Now we're in speculative territory, but it's the kind that excites astronomers and fuels TED Talks. Intelligent life refers to species capable of abstract thought, tool use, communication, and eventually technology. They would be capable of altering their environment, sending or receiving signals, and possibly venturing into space. This is the life we most often think of when we say aliens. But here's the kicker. On Earth, technological civilization has only existed for a blink of an eye. Roughly 100 years of radio broadcasting, out of 4.5 billion years of planetary history. The chances of another civilization existing at the same time as ours and being close enough for mutual detection, well, it's a bit like two needles trying to find each other in a galaxy-sized haystack, while blindfolded, during a solar storm. Yet we search, and not without reason. Our species is obsessed with finding other minds in the universe because we assume intelligence is the apex of evolution, the natural destination of any life form given enough time and resources. It's a comforting thought, albeit a bit arrogant. For all we know, intelligence might be a rare side effect, not an evolutionary inevitability. Dinosaurs ruled Earth for 160 million years and never built a space telescope. Humans have been around for a few 100,000, and already we've nearly wiped ourselves out multiple times using weapons we built ourselves. So perhaps intelligence isn't nature's goal. It might even be a mistake she doesn't repeat often. There's also growing interest in what's sometimes referred to as post-biological life, intelligent beings that no longer rely on organic bodies. If a civilization advances far enough, it might merge with its machines, uploading consciousness into synthetic systems that are far more durable than any flesh-based organism. These hypothetical entities wouldn't need atmospheres, water, or even planets. They could live in deep space, harnessing starlight and floating silently through the galaxy, utterly uninterested in chatting with noisy carbon units like us. In fact, they may have decided long ago that silence is safer than being noticed, a cosmic version of locking the door and pretending you're not home. So, when we ask if aliens exist, we're really asking, does any form of life exist beyond Earth? Microbial, complex, intelligent, or something we can't even imagine? We're trying to define not just life as we know it, but life as it might be. That includes chemical possibilities we've never encountered, environments we can barely simulate, and evolutionary paths that diverge from ours before Earth, even at continents. This is why the search for alien life is not just a hunt for UFOs. It's a multidisciplinary scientific endeavor that touches on biology, chemistry, planetary science, physics, computer modeling, and yes, sometimes a bit of philosophy. It challenges us to question what it means to be alive, what it means to be intelligent, and whether those definitions are too Earth-centric to apply elsewhere. In summary, the concept of extraterrestrial life is far broader and far more fascinating than popular culture would have you believe. It's not about humanoid beings with agendas and advanced weaponry. It's about understanding life in the most expansive, universal sense. And while we haven't found it yet, the definitions we build now will determine how we recognize it when we do. Because the truth is, if alien life exists, it probably won't look like us, think like us, or behave like us. It might not even notice us. But the universe is a big place. It would be the height of cosmic ego to assume it was built for us alone. Before we even begin to talk seriously about the probability of alien life, we need to appreciate the sheer, mind-boggling scale of the universe. Most people vaguely know that the universe is big. That's about as helpful as saying the Pacific Ocean is wet. The truth is, it's so incomprehensibly vast that our primate brains really struggle to hold the full picture in mind without short-circuiting. Fortunately, science is here to break things down in a way that's at least marginally less overwhelming, though still pretty humbling. Let's begin with our home, Earth. It's a medium-sized rocky planet orbiting a relatively ordinary star, our Sun, which is one of approximately 100 to 400 billion stars in the Milky Way galaxy. That's our galactic backyard. Now, the Milky Way is just one galaxy in the observable universe. Current estimates suggest there are at least 2 trillion galaxies out there. Multiply those two numbers together, trillions of galaxies, each with hundreds of billions of stars, and you start to see why the idea of Earth being the only place where life happens starts to feel just a tad self-centered. Now let's zoom in a bit. Among all these stars, a large fraction, perhaps most, have planets. This wasn't always considered a given. For centuries, the idea of planets orbiting other stars was purely theoretical. Then in the 1990s, we started finding them. First a few, then dozens, then hundreds, and now thousands. As of the time of writing, we've confirmed over 5,000 exoplanets, with many more candidates under observation. And we've only been looking properly for a couple of decades. If our current detection methods were fishing nets, we'd be using one the size of a tennis racket in an ocean the size of the universe, and we're still catching fish. Among these exoplanets, a certain number exist in what's known as the habitable zone, sometimes called the Goldilocks zone. Not too hot, not too cold, just right for liquid water. The presence of liquid water, as far as we know, is a pretty strong requirement for life. It's not that life must have water, but on Earth it always does, and since we're starting with a sample size of 1, water is our safest bet for now. Based on Kepler Space Telescope data, it's estimated that about 1 in 5 Sun-like stars may have a planet in the habitable zone. Given how many Sun-like stars there are, that means tens of billions of potentially habitable planets in our galaxy alone. Let's pause to emphasize that billions of potentially Earth-like planets in the Milky Way galaxy. And remember, the Milky Way is just one of at least 2 trillion galaxies. If your eyebrows aren't at least halfway up your forehead by now, check your pulse. So, statistically speaking, the existence of alien life, at least in its simpler forms, is not only possible, it's almost absurdly likely. When you do the math, the idea that we are alone starts to look not like a conclusion drawn from evidence, but a very fragile assumption clinging to anthropocentric comfort. Because yes, life may be rare. Intelligent life may be even rarer. But so is winning the lottery, and the universe has had 13.8 billion years to buy tickets. And yet, we haven't found anything. No radio signals. No spacecraft. No strange structures blotting out starlight. It's very quiet out there. This leads directly into what's famously known as the Fermi paradox, which we'll explore in detail later. But for now, suffice it to say that the silence doesn't contradict the probabilities. It may just mean we're still missing a huge piece of the puzzle. Maybe civilizations don't last long enough to become detectable. Maybe they're using communication methods we don't recognize. Maybe they're too far away. Or maybe, just maybe, they've already passed us by and decided we weren't worth the long-distance charges. But let's not get ahead of ourselves. Let's return to the probabilities. Beyond the famous Drake equation, which we'll cover in its own section, scientists have used various models to estimate the likelihood of life in the universe. These models factor in things like star formation rates, planetary system frequency, and the time needed for life to evolve. The conclusions vary wildly, from "we're probably surrounded by microbial life" to "intelligent aliens are basically unicorns with Wi-Fi." The range is so broad because, frankly, we don't have enough data. It's like trying to calculate the average number of trees in a forest after looking at one leaf. Still, even the most conservative models tend to agree. The universe is so vast, and the conditions for life so widespread, that life elsewhere is probable. The real debate is about the type, complexity, and detectability of that life. Interestingly, some scientists argue that life might be the rule, not the exception. If the origin of life is a natural outcome of chemistry under the right conditions, then the universe could be teeming with living worlds. The issue then becomes not whether life exists, but whether it ever develops into something that can say, "hello" from the other side. The jump from bacteria to Beyoncé is, apparently, a long and treacherous one. Moreover, recent discoveries have only added fuel to the fire. We've found organic molecules on comets, signs of water on Mars, and bizarre microbes here on Earth that survive in conditions once thought to be incompatible with life. The boundaries of what's habitable have expanded dramatically, and every time that boundary shifts, the probability of alien life ticks upward. Still, it's worth noting that probability is not proof. Just because the numbers are in life's favor doesn't mean we're guaranteed to find it. But what probability does offer is a compelling reason to keep looking. It tells us that this is not a futile search for a cosmic ghost, but a scientific endeavor with real statistical backing. And let's be honest, the alternative is almost too bleak to consider. If life exists only here, on this one rocky planet circling a nondescript star in an unremarkable arm of a very average galaxy, then life is not just rare, it's cosmically unique. That would make Earth not a blue marble in space, but the only marble. And that would make our responsibilities here even more enormous than we thought. So, when people say the universe is too big for us to be alone, they're not just repeating a feel-good phrase. They're channeling a statistically grounded reality. The numbers favor life. The chemistry favors life. And as far as we can tell, the universe doesn't seem particularly interested in playing favorites. In the end, the question isn't whether the universe is big enough to host life. It's whether we're clever enough, patient enough, and open-minded enough to recognize it when we finally see it. Because chances are, the cosmos is not empty. It's just waiting for us to catch up. If you're planning to find life elsewhere in the universe, the first step is to know what you're looking for. But right after that comes the equally important question: what are the conditions under which life can exist? It's like trying to find a rare animal. You have to know its habitat. Unfortunately, when it comes to alien life, we can't exactly pop over to Alpha Centauri and take water samples. So we use the best model we have, Earth. And lucky for us, Earth is bursting at the seams with life, in every nook, cranny, and acidic crevice. But let's not get ahead of ourselves and assume that all life has to be Earth-like. While Earth is the only place we know life exists, that doesn't necessarily mean it's the only type of life that can exist. Still, when scientists search for alien life, they tend to start with the conditions that made life possible here. Think of it as using Earth as a cosmic recipe book, with the understanding that alien cooks might be experimenting with some very different ingredients, or wildly different ovens. So what are the ingredients? Let's begin with the biggest celebrity in the biochemistry world, liquid water. Everywhere we find life on Earth, we find water. It's the universal solvent, a medium in which complex molecules can float, collide, react, and sometimes, miraculously, self-organize into cells. Without water, life as we know it doesn't just struggle, it basically stops. That's why so much of our planetary exploration, on Mars, Europa, Enceladus, and beyond, is focused on following the water. If you find liquid water, you've just ticked off one of the most important boxes on the habitability checklist. Now, some might say, well, who's to say life elsewhere needs water? And that's a valid point. Maybe aliens slosh around in liquid methane or ethane. Or perhaps they're just sentient clouds of plasma that laugh at the idea of solvents. But until we have direct evidence of such life, we're sticking with what we know, and what we know works. Water provides a stable, chemically reactive environment over a broad temperature range. Plus, it's relatively abundant in the universe. So no, it's not just hydrating, it's statistically promising. Next on the list, essential chemical elements, particularly carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, known collectively in biology as CHNOPs. These elements are the building blocks of amino acids, proteins, DNA, cell membranes, basically everything you need to go from inert mud to something that argues on the internet. Why carbon? Because it forms stable, complex molecules with an almost annoying level of versatility. Silicon is sometimes brought up as an alternative, but carbon wins hands down in the molecular Lego department. These elements are not just Earth-exclusive party favors. They're actually abundant in the cosmos, found in interstellar gas clouds, meteorites, and even in the atmospheres of other planets. So, the raw materials for life are not rare. In fact, they're so common that the real question becomes not, are the ingredients there, but is the kitchen in working order? That brings us to another essential factor, energy. Life needs energy to stay alive, grow, reproduce, and occasionally do things like write 1,000-word essays about itself. On Earth, the main source of energy is the sun. Photosynthesis harnesses sunlight to build organic molecules, and everything else either eats plants or eats something that ate plants. But sunlight isn't the only game in town. At the bottom of Earth's oceans, far from any sunlight, entire ecosystems thrive around hydrothermal vents. These deep-sea communities are powered by chemosynthesis, using chemical reactions from vent emissions instead of light. This is important. It tells us that a planet or moon doesn't need to have sunlight to support life. As long as there's some source of usable energy, whether from a star, geothermal activity, radioactive decay, or chemical gradients, life has a shot. Europa and Enceladus, icy moons with possible subsurface oceans and internal heating, are perfect examples. They don't look like paradise from the outside, but beneath their icy crusts, they may be hiding warm, watery worlds where alien microbes are getting along just fine. Thank you very much. The next condition, a stable environment. Life needs time, not 5 minutes, not 5 years, but often billions of years, to evolve from simple molecules into something complex, let alone intelligent. If a planet's surface is constantly being sterilized by asteroid impacts, cosmic radiation, or violent solar flares, life may never get the chance to advance. That's one reason Earth is so special, not just because it has the right ingredients, but because it's been relatively stable for a very long time. Of course, we've had a few extinction events here and there, looking at you, dinosaurs. But overall, Earth has provided a consistently livable environment for billions of years. That's the biological equivalent of winning the cosmic lottery, and then winning it again every day for the next 3.5 billion years. This is where a planet's magnetic field and atmosphere come into play. Earth's magnetic field shields the surface from deadly solar and cosmic radiation. Its atmosphere traps heat, allows liquid water, and protects against smaller meteorites. These may sound like technicalities, but they're absolutely vital. Without a magnetic field, Earth's surface would be as sterile as Mars. Without an atmosphere, it'd be even worse, because there wouldn't be a surface, just vacuum and regret. Now, one can argue that life might evolve under different conditions entirely. Maybe alien organisms breathe hydrogen sulfide instead of oxygen. Maybe they thrive in extreme pressures or intense radiation. And we shouldn't dismiss those ideas, especially since Earth hosts extremophiles that survive in boiling acid, freezing salt water, and even nuclear reactors. The discovery of these organisms has massively expanded our understanding of what's habitable. What used to be considered deadly, life-prohibiting conditions are now just niche environments for especially tough microbes. So yes, while we continue to focus on finding Earth-like conditions, it's worth keeping an open mind. The laws of chemistry and physics are universal, but evolution tends to get a little creative. It's possible that life is far more adaptable and weird than we ever imagined. To sum it all up, when scientists search for alien life, they're looking for the habitability trifecta: liquid water, the right chemistry, and an energy source, all within a reasonably stable environment. This doesn't guarantee life, of course, but it stacks the odds heavily in its favor. Just like Earth didn't magically spawn life overnight, we don't expect to find it under every rock on Mars or in every gas cloud. But where these conditions exist, life could follow. And considering the sheer number of planets and moons out there, even rare conditions can be common in absolute numbers. In the end, the universe doesn't promise life, but it certainly seems to encourage it. And if life does find a way, as Jeff Goldblum so scientifically put it, then it's only a matter of time, tools, and patience before we stumble across it in some salty ocean under an icy crust, or wafting through the atmosphere of a rogue planet, probably judging us silently from a safe distance. If Earth isn't the only home for life in the universe, and all signs are pointing to that being a very real possibility, then the next question is, Where else should we be looking? Enter the exoplanet. Once an idea confined to science fiction and overly optimistic textbooks, exoplanets are now front and center in astronomy's quest to answer the age-old question: are we alone? And the more we look, the more we find. Turns out the universe has been holding out on us all along. An exoplanet is simply a planet that orbits a star outside of our solar system. For a long time, their existence was assumed but unproven. After all, why should our star, the Sun, be the only one with a planetary entourage? Still, it wasn't until 1992 that the first confirmed exoplanets were detected, orbiting, of all things, a pulsar, a highly magnetized, rapidly rotating neutron star. This was both unexpected and deeply confusing. It's like discovering the first birds not in a forest, but nesting in an active volcano. Then in 1995, we found 51 Pegasi b, the first exoplanet orbiting a Sun-like star. Since then, the floodgates have opened. As of now, we've confirmed over 5,000 exoplanets, and that number climbs with every new telescope pointed skyward. It turns out that planets are not rare at all. They're the rule, not the exception. Statistically speaking, most stars have at least one. Some have entire systems of them. In other words, we went from, "Are there other planets out there?" to, "Wow, we are terrible at noticing planets." Detecting them, though, isn't exactly easy. We can't usually see exoplanets directly. They're tiny and dim compared to their host stars, so astronomers use a few clever indirect methods to catch them in the act. The most common technique is the transit method, which involves watching a star and waiting for it to dim ever so slightly as a planet crosses or transits in front of it. Think of it like trying to detect a gnat passing in front of a lighthouse from several miles away. But it works. This method was made famous by NASA's Kepler Space Telescope, which stared at a single patch of sky and gave us thousands of new planetary candidates. Then came TESS, Transiting Exoplanet Survey Satellite, scanning nearly the entire sky. And now, we have the James Webb Space Telescope, JWST, which can not only detect exoplanets, but analyze the composition of their atmospheres. Yes, we are now in the business of sniffing the air of planets hundreds of light years away. Welcome to the future. Another detection method is the radial velocity method, or the wobble method. As a planet orbits its star, its gravity tugs slightly on the star, causing it to wobble very slightly. This wobble can be measured via the Doppler shift in the star's light. It's not the most intuitive form of celestial dance analysis, but it gets the job done. Now, among these thousands of exoplanets, we are particularly interested in a select few, those that exist in their star's habitable zone, also known as the Goldilocks zone. You know the story: not too hot, not too cold, but just right, for liquid water, that is. If a planet is too close to its star, water boils off, and you get a scorched hellscape like Venus. Too far, and it's a frozen wasteland like Pluto, sorry, dwarf planet Pluto. But somewhere in between, water can remain liquid, arguably the universal solvent for life as we know it. But let's be clear, being in the habitable zone doesn't guarantee habitability. That's just the start. It's like saying a house is located near a grocery store. It doesn't mean the plumbing works or the roof doesn't leak. A planet's actual habitability depends on dozens of other factors: atmosphere, magnetic field, plate tectonics, and whether or not it's being pelted by solar flares like a punching bag. Still, finding planets in the habitable zone is the first major filter in narrowing down the search. And we've found quite a few. Some of the stars in the neighborhood have caught our attention for hosting particularly interesting candidates. Proxima Centauri b, orbiting the closest star to the Sun, a mere 4.24 light-years away. This rocky planet lies within its star's habitable zone. Sounds great, except its star is a red dwarf known for violent flare activity, which could strip away any atmosphere faster than you can say ionosphere. TRAPPIST, one system. This system contains 7 Earth-sized planets, with at least 3 in the habitable zone. Located about 40 light-years away, it's like a cosmic family of possibly watery worlds. Again, the star is a red dwarf, so the flare problem applies here too, but the potential is tantalizing. Kepler 442b, Kepler 62f, and LHS 1140b. Among dozens of other promising candidates, these planets are all within habitable zones and are of the right size and composition. We don't know if they have atmospheres, oceans, or anything living on them, but they check all the boxes for interesting. Now, with the James Webb Telescope in action, we're starting to move beyond just finding these planets. We're starting to characterize them. By analyzing the spectra of light filtered through their atmospheres during a transit, we can look for molecules like water vapor, methane, carbon dioxide, ozone, and, just maybe, biosignatures. That is, chemical clues that suggest life is doing something metabolic down there. For instance, a planet with high levels of oxygen and methane in its atmosphere might raise some eyebrows. On Earth, those gases shouldn't coexist in such quantities unless life is constantly replenishing them. So if we see something similar out there, it might be worth sending a very polite, very distant postcard that says, "Hi, we noticed your atmosphere. Nice chemistry. But, as always, we must proceed with caution. Life isn't the only thing that can produce these gases. Volcanic activity, photochemistry, and other abiotic processes can mimic biosignatures. The line between alien life and overexcited data interpretation can be surprisingly thin. Still, exoplanet science is young, and it's progressing at light speed, figuratively, unfortunately. Just 20 years ago, the idea of even knowing about other Earth-like planets was wishful thinking. Now, we're comparing their atmospheres, tracking their orbits, and building next-generation telescopes that will one day let us take actual images of them. Yes, photos of other worlds. If that doesn't qualify as scientific sorcery, I don't know what does. So, in conclusion, the search for exoplanets, especially those in habitable zones, isn't just about ticking boxes or updating catalogs. It's the groundwork for something far more profound. Each new planet is a candidate, a possible home, a quiet maybe in the cosmic noise. And as we refine our tools and deepen our understanding, we inch ever closer to the day when one of those maybes becomes a resounding yes. We haven't found Earth 2.0 yet, but we know it's out there. And when we do find it, let's hope they have decent Wi-Fi and slightly better decision-making than we do. If the search for alien life were a game, astrobiology would be the official referee, coach, playbook author, and occasionally the commentator yelling, "We may have found something," before the replay confirms it was, in fact, just a rock. But seriously, astrobiology is the scientific field at the very heart of the question, do aliens exist? It's the interdisciplinary study of life in the universe, its origin, evolution, distribution, and future. And yes, that's a mouthful, but it's a necessary one when you're trying to answer one of the most profound questions in human history using a toolkit that spans biology, chemistry, physics, planetary science, geology, oceanography, and a touch of existential curiosity. At its core, astrobiology is about possibility. It doesn't assume life is out there, but it does ask rigorously and persistently, could it be? And if so, what would it look like? How would it survive? And where should we look for it? Unlike some fields of science, astrobiology doesn't yet have a direct object of study. We have no confirmed alien organisms. We check the fridge twice. So astrobiologists spend most of their time studying life on Earth, especially in extreme environments, as a proxy for what might exist elsewhere. These include the boiling acid pools of Yellowstone, the ice-covered lakes of Antarctica, the crushing pressure zones of the Mariana Trench, and, for sheer audacity, even the insides of nuclear reactors. It turns out, life is absurdly good at adapting, and astrobiologists are constantly discovering new ways Earth's organisms thumb their noses at what we used to call inhospitable. These extremophiles, organisms that thrive where most life would promptly curl up and die, are the closest things we currently have to analogs for alien life. Take Deinococcus radiodurans, affectionately nicknamed Conan the bacterium. It can survive thousands of times the radiation that would kill a human and even reassemble its DNA after being shattered. Or consider the tardigrade, aka the water bear. It survives freezing, boiling, starvation, dehydration, and yes, even space. These aren't just interesting party tricks. They are case studies for how robust life can be. Astrobiologists study such organisms to expand the definition of habitability. A few decades ago, the idea that life could exist anywhere except on a temperate, Earth-like planet was considered laughable. Now, we're seriously considering moons with subsurface oceans, rogue planets without stars, and even the upper atmospheres of gas giants. In fact, one of the driving themes of astrobiology is that the universe may be way more hospitable to life than we thought. It's not a question of whether conditions exist. It's a question of whether we're clever enough to recognize them when we see them. And that brings us to biosignatures, indicators that life might be present. These can be chemical, physical, or geological. For example, on Earth, the simultaneous presence of oxygen and methane in the atmosphere is a strong biosignature. These gases react with each other and would vanish quickly without constant replenishment by biological processes. If we found a similar atmosphere on an exoplanet, the champagne corks in astrobiology departments would pop quietly because science still needs to be peer-reviewed. But inside, celebration. Biosignatures don't just come from gas analysis. Patterns of surface reflectance, seasonal changes in atmospheric composition, isotopic ratios in rock samples. These too can hint at life. Some researchers are even working on detecting technosignatures, byproducts of technology, like artificial pollutants or unusual heat emissions. If you ever wondered whether we might detect alien civilization by noticing their version of climate change, congratulations. You've just been thinking like an astrobiologist, albeit one with a slightly cynical sense of humor. So where do astrobiologists actually look? At the moment, the solar system provides several tantalizing options. Mars, the red planet, is basically the solar system's drama queen when it comes to the search for life. It's dry, cold, and irradiated, but also holds evidence of ancient rivers, seasonal methane spikes, and possibly even briny underground lakes. If microbes ever lived, or still live, on Mars, they're probably hiding below the surface, away from the cosmic microwave spotlight. Europa, a moon of Jupiter, beneath its thick shell of ice lies a vast liquid ocean, possibly with more water than Earth. It's kept warm by tidal heating, gravitational friction that prevents the ocean from freezing solid. If any place in the solar system screams potential alien aquarium, it's Europa. Enceladus, a moon of Saturn similar to Europa, Enceladus has a subsurface ocean, and it vents water into space via geysers. These plumes have already been sampled by spacecraft, looking at you, Cassini, and the results show organic compounds, salts, and even hints of hydrothermal activity. It's like a smoothie of possible life ingredients being conveniently sprayed into space for us to analyze. How thoughtful. Titan, another moon of Saturn, Titan is weird in the best possible way. It has lakes and rivers, but not of water. They're made of liquid methane and ethane, flowing across a landscape of frozen hydrocarbons. While this is not a place where Earth-style life would enjoy itself, Titan presents a real possibility for alternative biochemistry. Some researchers believe Titan might even host exotic life forms that swim in methane and use entirely different solvent systems. If true, that would be a discovery so paradigm-shifting, it would make Darwin sit up in his grave. Astrobiologists also model the origin of life itself. One big question is, did life on Earth arise independently, or did it get a little head start from somewhere else? The theory of panspermia suggests that life, or its building blocks, might have arrived here on meteorites from elsewhere. It sounds like science fiction until you realize that we've actually found amino acids and organic molecules on comets and meteorites. So Earth's early oceans may have been less of a primordial soup and more of a space delivery service. Of course, despite the excitement, astrobiology is still waiting for its first confirmed success story. No alien microbe, no extraterrestrial worm, not even a suspiciously intelligent fungus. Yet, but the work is anything but idle. Every new mission, every atmospheric reading from a distant exoplanet, every new extremophile discovered on Earth adds to the picture. It's like assembling a 1,000-piece puzzle when you're not entirely sure what the final image is supposed to be, or if some of the pieces are invisible. And that's part of the beauty of astrobiology. It's the science of the in-between, between disciplines, between planets, and between what we know and what we dare to imagine. It embraces the mystery while staying rigorously grounded in evidence. It teaches us that life may not be an anomaly, but a natural outcome of the right conditions. And even if we never find a single alien microbe, astrobiology still gives us a deeper appreciation of just how ridiculously lucky we are to be alive on this watery rock orbiting an average star. So no, astrobiologists haven't found aliens yet, but give them time. They're asking the right questions, exploring the right environments, and building the right tools. And when we finally get that undeniable signal, or that fossilized microbe, or that strangely intelligent methane-based fish swimming on Titan, they'll be the first to say, "Told you so." Before we go running around the universe searching for alien microbes, or, if we're lucky, some awkwardly polite alien philosophers, it makes sense to first examine the one place where we know life exists, right here on Earth. Yes, our own squishy, noisy, oxygen-rich planet, where the locals can't even agree on pizza toppings, managed to create conscious beings who now wonder if they're alone in the cosmos. So how did life start here? And how exactly did we go from primordial soup to tweeting? The origin of life on Earth is one of science's most compelling, frustrating, and deliciously mysterious questions. We call it abiogenesis, the process by which life arises naturally from non-living matter. And to be clear, this is not the same as evolution. Evolution explains how life changes over time. Abiogenesis explains how it began in the first place. It's like the difference between building a car and racing it around the track, two very different challenges. The current scientific consensus is that life began on Earth around 3.5 to 4 billion years ago, which, in case you're counting, is nearly 1 billion years after the planet itself formed. That might seem like a leisurely start, but given the fact that early Earth was constantly being bombarded by comets, asteroids, and probably occasional chunks of the moon trying to move back in, it's amazing life got going at all. But once things cooled down and liquid water pooled on the surface, Earth essentially became a giant chemistry lab with no safety regulations. Here's where it gets juicy. Under the right conditions, simple molecules like methane, ammonia, and water vapor can combine to form amino acids, the building blocks of proteins, and eventually nucleic acids like RNA and DNA. This isn't just speculation, it's been demonstrated in the lab. In the famous Miller-Urey experiment of 1952, scientists recreated early Earth's atmosphere in a closed system and hit it with electric sparks to simulate lightning. After a few days of zapping, lo and behold, the solution turned brown and was found to contain amino acids. This was the scientific equivalent of baking a cake by throwing flour and eggs into a thunderstorm and hoping for the best, and it worked. Still, making amino acids is only the beginning. Life needs self-replication, metabolism, and a container, aka a cell membrane, to separate itself from the chaos outside. Somehow, these pieces came together into the first protocells, microscopic blobs of chemistry that could replicate and evolve. No one's managed to create a fully self-replicating protocell in the lab yet, but we're getting closer. Nature, it turns out, had billions of years and the entire planet to run experiments. Scientists have to do it with a coffee budget and grant deadlines. Now, let's talk about the first actual life forms. These were not dinosaurs, or even cute squishy fish. The earliest life on Earth was probably simple, single-celled prokaryotes, like bacteria. These microscopic pioneers showed up at least 3.5 billion years ago, possibly even earlier. Some of their fossils can be found in structures called stromatolites, which are layered mounds built by microbial communities that somehow still exist today in places like Shark Bay, Australia. Evolution may have changed a lot, but apparently, forming slimy mats is a winning strategy that never goes out of style. For over a billion years, life on Earth consisted of nothing more than microbes. That's right. For most of our planet's history, it was a bacterial empire. And why not? Bacteria are astonishingly efficient, adaptable, and capable of thriving in environments that would kill pretty much everything else. They don't need sunlight. They don't need oxygen. Some don't even need other bacteria to hang out with. They were, and still are, the ultimate survivalists. Then came a major leap forward. The emergence of eukaryotic cells, more complex cells with nuclei and organelles. These cells are believed to have evolved via endosymbiosis, a sort of microbial merger and acquisition event where one cell engulfed another, and instead of digesting it, they decided to work together. This gave rise to mitochondria, the tiny power plants inside our cells, and later, in plants, chloroplasts. It was like life discovering not only electricity, but corporate synergy. With eukaryotic cells in place, evolution took off like a rocket. Over the next billion years, we saw the emergence of multicellularity, which eventually led to the first plants, fungi, and animals. Around 600 million years ago, the Cambrian explosion occurred, a dramatic period in which the fossil record shows an incredible burst of biological diversity. Suddenly, the oceans were full of weird, experimental creatures, many of which had no idea how to survive. Evolution is, after all, a trial-and-error business. From there, the tree of life expanded in every direction. Some branches led to fish, others to insects, others still to mammals. One branch led to primates, then hominins, then eventually to a species capable of building space telescopes and arguing online about whether Pluto is a planet. Spoiler, it's complicated. Now let's circle back. What does this evolutionary journey tell us about alien life? First, life starts simple. No matter how imaginative our sci-fi stories get, it's almost certain that alien life, if it exists, will have started with microbes or microbial analogs. That's not to say intelligent life can't evolve elsewhere. It just takes time, environmental stability, and a few lucky mass extinctions to shake things up. Looking at you, asteroid that ended the dinosaurs. Second, life is resilient. Once it starts, it finds a way to persist, even in the harshest of conditions. The adaptability seen in Earth organisms, from boiling vents to radioactive waste, suggests that once life gains a foothold, it's hard to get rid of. Encouraging if you're looking for it elsewhere. Slightly terrifying if you were hoping Earth's ecosystem had a reset button. Finally, life is inevitable looking. Given the right conditions, the chemistry of life seems to want to happen. Carbon is just so good at making complex molecules. Water is an amazing solvent. Given enough time, complexity increases. Evolution favors survival, and complexity often gives organisms the edge they need. So, does the origin and evolution of life on Earth prove that aliens exist? Of course not. But it strongly suggests that life isn't some cosmic accident, either. If the same ingredients, under the same conditions, repeatedly create similar results on Earth, why shouldn't they elsewhere? To put it a bit sarcastically, if the universe didn't have life elsewhere, it would be a pretty inefficient use of space. We're talking about billions of galaxies, each with billions of stars, many with planets, some of which resemble Earth. If Earth is the only place where chemistry got bored and invented consciousness, that's either an extraordinary stroke of luck or, well, maybe we're just not looking hard enough yet. So next time you look up at the night sky and wonder if we're alone, remember, life here started with molecules bumping into each other in a lukewarm pond. From there, it became bacteria, then fish, then eventually something that learned how to write essays about the origin of life. That trajectory might not be unique. It's humbling and just a bit thrilling to think that somewhere out there, another planet might be going through its own slow climb from slime to sophistication. We just haven't met them yet. If there were ever a piece of math that launched 1,000 debates, ignited countless late-night dorm room conversations, and inspired an unhealthy number of sci-fi movies, it's the Drake equation. Created in 1961 by radio astronomer Frank Drake, the equation was never intended to provide a final answer to the question, are we alone? Instead, it was meant as a framework, an elegant little roadmap to help scientists think through all the factors that might influence the number of communicative alien civilizations in our galaxy. And by communicative, we don't mean aliens who write Shakespeare or send us philosophical TikToks. We mean civilizations capable of emitting detectable signals into space, like radio waves or laser beams, or maybe even the occasional ill-advised death ray. The Drake equation looks like this. N equals our asterisk times Fp times Ne times Fl times phi times Fc times L. Let's break that down. Each variable represents a step in the cosmic chain leading from stars to aliens with radio telescopes. N is the number of civilizations in the Milky Way with which we might be able to communicate. That's the ultimate number we're trying to estimate. Though if it turns out to be less than 1, we may want to take up knitting instead of interstellar diplomacy. Our asterisk is the average rate of star formation per year in our galaxy. Current estimates put this somewhere between 1 and 3 new stars per year. The Milky Way is nothing if not productive, basically a galactic baby factory. Fp is the fraction of those stars that have planetary systems. This one used to be a big unknown, but thanks to exoplanet hunting missions like Kepler and TESS, we now know that planetary systems are incredibly common. Conservatively, Fp is at least 0.8, maybe closer to 1. In short, stars love having planets. It's basically their accessory of choice. Any is the number of those planets per system that could potentially support life. This is usually interpreted as the number of Earth-like planets in the habitable zone where liquid water can exist. The estimates vary, but a common guess is around 0.2 to 0.5 per planetary system. Again, it depends on how picky you are. If your idea of habitable is as cozy as Earth, then sure, 0.2. If you're more into toxic, lava-covered death worlds where tardigrades might thrive, then any gets a bump. FL is the fraction of habitable planets on which life actually arises. This is where things start to get philosophical because we only have one known data point, Earth. And since Earth isn't a controlled experiment, we don't know if life popped up quickly here because it's easy, or if we just hit the biological jackpot. Some scientists argue that FL could be close to 1. Life arises wherever it can. Others say it might be vanishingly small, and we're the fluke. Either way, this variable tends to carry a lot of existential baggage. Phi is the fraction of life-bearing planets where intelligent life evolves. Because bacteria are great and all, but they're not exactly designing radio telescopes. This is another question mark. Intelligence may be an evolutionary accident, or, depending on how you feel about the average internet comment section, possibly a terrible idea. It took about 4 billion years for humans to show up on Earth, which suggests this step is slow and rare. Or maybe nature was just waiting for the right primate with opposable thumbs and emotional issues. FC is the fraction of intelligent civilizations that develop technology capable of communication across interstellar distances. And just to make things more complicated, this also assumes they want to communicate. It's entirely possible that most intelligent species go through a short techno phase before either blowing themselves up or switching to a post-verbal, meditation-based society where everyone just vibes silently for eternity. In that case, FC could be low. L is the average lifespan of such civilizations, specifically, how long they emit detectable signals. This is a big one. If civilizations tend to self-destruct, say, via war, climate collapse, AI uprising, or bad reality TV, then L could be short, maybe just a few hundred years. But if they manage to stabilize and go full Star Trek, L could be thousands or even millions of years. And since the galaxy is billions of years old, even a modest L gives us a decent chance of overlapping with someone else's signal. So what does all this give us? Well, that depends entirely on what numbers you plug in. Frank Drake himself originally estimated N to be around 10,000. Which sounds exciting until you realize that even with that many civilizations, they might still be light years apart, quietly existing, broadcasting into the void, never knowing we're here. Like a really sad version of a dating app, where everyone's too far away to meet for coffee. On the more skeptical end, some scientists, like the late Michael Hart, plug in low values for FL, Phi, and L, and end up with N equals 1. That is us. Just us. Echoes in a cosmic cathedral. But others remain more optimistic. Astronomer Sarah Seeger once proposed a version of the Drake equation focused solely on biosignature detection, replacing intelligent life with just any kind of life that can alter a planet's atmosphere. By that logic, the chances of finding life, if not intelligent life, go way up. One reason the Drake equation remains relevant is that it forces us to ask the right questions. How common are Earth-like planets? How fast does life emerge? Is intelligence inevitable or a freak accident? Do civilizations survive their own progress? Are we even listening correctly? It also subtly reminds us of something else. We don't yet know enough to answer these questions confidently. That's not a weakness. It's the whole point. The Drake equation is not a final solution. It's a scientific thought experiment that continues to evolve as we learn more. And thanks to advances in astronomy, planetary science, and AI, we're narrowing down the variables. In fact, some modern interpretations suggest that, unless L is catastrophically short, the odds are pretty good that other civilizations exist, or have existed, in our galaxy. Of course, this brings us right to the next question. If they're out there, why haven't we heard from them? Enter the Fermi paradox, the universe's biggest unsolved mystery, and the topic of our next section. So let's say you followed the logic of the Drake equation, nodded sagely, and concluded that the galaxy should be crawling with alien civilizations. Great. But then a little voice in the back of your mind, maybe channeling your inner skeptic or just a slightly paranoid version of Spock, asks, if that's true, where is everybody? That question, famously attributed to physicist Enrico Fermi, is the heart of what we now call the Fermi paradox. Fermi reportedly asked this over lunch in the 1950s after a discussion about UFOs, space travel, and the likelihood of intelligent life. One minute they were chatting about little green men, the next he drops the mic with, "But where is everybody?" Cue dramatic silence and a decades-long scientific conundrum. The paradox goes like this. The universe is vast, about 13.8 billion years old and packed with billions of galaxies, each containing billions of stars and likely even more planets. Statistically speaking, there should be many opportunities for life to emerge, evolve intelligence, and develop the ability to explore or communicate. And some of these civilizations could have had millions of years of a head start. And yet, we see nothing. No spaceships, no alien emails, no interstellar billboards offering galactic broadband. The skies remain stubbornly silent. So what gives? Scientists, philosophers, and more than a few conspiracy theorists have offered dozens of possible solutions, and they generally fall into a few broad categories. Maybe they're not there, maybe they're not talking, or maybe we're too dumb to notice. Let's explore a few of the most popular and unsettling explanations. 1. We're alone, aka the depressingly empty universe hypothesis. One simple answer. Maybe intelligent life really is that rare. The Great Filter Theory, introduced by economist Robin Hanson, suggests that somewhere along the path from simple molecules to advanced spacefaring civilizations, there's a big, nasty hurdle that's almost impossible to cross. It could be that abiogenesis is vanishingly rare, or that intelligent life usually self-destructs before getting very far. Hello, nuclear weapons, climate change, and social media. If the Great Filter is behind us, congrats, we're exceptional. If it's ahead of us, well, maybe let's not find out. 2. They're hiding, aka the zoo hypothesis. Maybe aliens are already here, watching us like we're in a cosmic reality show. This is the zoo hypothesis, and it suggests advanced civilizations intentionally avoid contact with primitives like us, either out of ethical responsibility or simple disinterest. From their perspective, we're probably the galactic equivalent of a toddler banging rocks together and calling it culture. Why interfere when the Earthlings still haven't figured out basic cooperation? 3. We're too early or too late. Perhaps intelligent life is rare but not unique, and we just happen to be among the first to emerge. Civilizations could still be forming. Or maybe the glory days of galactic civilization were billions of years ago, and we missed the party. It's like arriving at the club at 10 a.m. or showing up after last call. Wrong place, wrong time. 4. They don't want to talk. Assuming aliens do exist, why would they try to communicate? It's a big assumption that any civilization would invest in broadcasting signals, just hoping someone picks them up. Maybe their version of progress isn't technological at all. Maybe they're post-biological, living in simulated realities, and the idea of radio waves and blinking lights seems hopelessly primitive. Or maybe they've learned that broadcasting your location is a bad idea. You never know which galactic neighbors are hungry. 5. Space is big, signals are weak. Another possibility: the signals are out there, but we just haven't looked long enough, in the right way, or with the right tools. The galaxy is enormous, and even light, our fastest messenger, takes thousands of years to cross it. We've only been scanning for alien signals for a few decades, in a limited range of frequencies, and often only for short windows. It's like trying to find a whisper in a hurricane with earmuffs on. 6. Advanced civilizations use different tech. We assume aliens would communicate via radio waves, because that's what we do. But what if they've moved on to something far more advanced? Laser pulses, neutrino beams, quantum entanglement. Technologies we either don't understand or don't know to look for. If you tried to send a text message to an ancient Roman and got mad when he didn't respond, whose fault is that, really? 7. They're already here, but undetected. Cue the X-Files music. Some theorists argue that aliens may already be present, as microscopic life, hidden probes, or cleverly disguised among us. Your coworker who only eats raw lettuce is looking suspicious. But while this idea makes for great cinema, the scientific evidence is essentially non-existent. Unidentified aerial phenomena, UAPs, have sparked renewed interest, but as of now, nothing has conclusively pointed to extraterrestrial origins. 8. Civilizations self-destruct. Here's a cheerful one. Maybe the reason the galaxy is quiet is because intelligence comes with a built-in expiration date. Nuclear war, runaway AI, ecological collapse. The list of potential civilization-ending disasters is long. If technological advancement tends to outpace wisdom, and let's be honest, we're not doing great on that front, then it's possible that most civilizations burn out quickly after reaching radio capability. 9. Interstellar travel is impossible or pointless. Even if there are thousands of civilizations, the sheer distance between stars is a massive barrier. It takes decades just to reach nearby stars with current tech, and even light-speed travel doesn't make it easy. Maybe galactic empires are only possible in sci-fi, and real civilizations just stick to their home systems, sending out the occasional lonely probe that no one ever finds. 10. We haven't recognized the signs. Perhaps the evidence is already here, but we lack the perspective or technology to recognize it. A strange signal might be dismissed as noise. An unusual exoplanet atmosphere might be a form of alien terraforming. Maybe intelligent life is so different from ours that we wouldn't recognize it even if it sent us a postcard. Ultimately, the Fermi paradox is unsettling because it combines hope and disappointment in equal measure. The universe seems designed to produce life, yet we find no one home. It suggests that either we're special or we're doomed, or both. Still, the paradox isn't a dead end, it's a challenge. It pushes science to explore harder, think more creatively, and refine our expectations. It reminds us that absence of evidence isn't evidence of absence. Just because we haven't heard from anyone doesn't mean they're not out there. Maybe they're using different frequencies. Maybe we're on the wrong channel. Or maybe they've been talking this whole time, and we just haven't been listening closely enough. So what's the answer? We don't know yet. But the Fermi paradox ensures we'll keep asking, and maybe one day we'll get a reply. If you've ever imagined scientists sitting around with massive headphones, scanning the skies for whispers from space, you're not too far off. Except, instead of headphones, we've got radio telescopes, and instead of whispers, we're searching for narrow bandwidth, non-random, artificial-looking signals that might say, "Hey, you're not alone." This is the realm of radio astronomy, And at its more adventurous frontier lies the SETI project, Search for Extraterrestrial Intelligence. It's a scientific initiative with a simple but wildly ambitious goal: detect signs of intelligent alien civilizations using electromagnetic signals. In other words, we're trying to catch aliens broadcasting their version of a cosmic mixtape, one that hopefully doesn't just loop whale sounds or the alien equivalent of elevator music. But let's back up a bit. Why radio waves? Why not, say, giant space billboards or smoke signals? Radio waves are perfect for long-distance interstellar communication. They're relatively easy to generate. They travel at the speed of light, and they can move through dust and gas without much trouble. Plus, they require relatively little energy to transmit and are less prone to interference across cosmic distances. In short, if aliens are even remotely practical, they'd probably use radio. And we're betting on that. The history of SETI goes back to the mid-20th century. One of the earliest scientific proposals came in 1959 from physicists Giuseppe Cacconi and Philip Morrison, who suggested using radio waves near the 1,420 MHz frequency, the natural emission line of neutral hydrogen. Why hydrogen? Because it's the most abundant element in the universe. Think of it as the universal hello frequency. If you're trying to be found, it's a good place to start broadcasting. Shortly after, in 1960, a young Frank Drake launched Project Ozma, the first modern SETI experiment. Using a 26-meter radio telescope in West Virginia, he aimed it at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for signs of artificial transmissions. He didn't hear anything, but it was the beginning of something big, an idea that refuses to die, no matter how many times the budget committee tries to kill it. Since then, SETI has evolved from one man's two-star experiment into a broad, global effort involving universities, observatories, and even citizen scientists. Let's talk about the heavy hitters. The Allen Telescope Array, ATA, located in California and funded in part by Microsoft co-founder Paul Allen, was designed specifically for SETI. It can listen to multiple targets at once, scanning thousands of star systems for any sign of intelligent signals. It's a real-time, always-on, alien listening machine. Unfortunately, due to funding issues, it hasn't always operated at full capacity, because even in the search for aliens, someone's always misplacing the checkbook. Another major player is the Breakthrough Listen initiative, launched in 2015 with a cool $100 million from billionaire Yuri Milner. This is by far the most ambitious and well-funded SETI effort to date. Using some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, Breakthrough Listen scans millions of stars, galaxies, and even fast radio bursts, FRBs, for any hint of a signal. To be clear, SETI doesn't believe aliens are out there. It simply asks, if they were, could we detect them? It's a hypothesis test, not a cult. The focus is on data, repeatability, and eliminating Earth-based interference, which, spoiler alert, turns out to be a lot harder than it sounds. We're constantly surrounded by a mess of signals: Wi-Fi, satellites, radar, TV broadcasts, all of which can mimic alien signals if you're not careful. This is why most discoveries turn out to be nothing more than reflections, glitches, or the occasional intern microwaving lunch near the equipment. True story from Parkes Observatory in 2015, SETI was briefly fooled by a microwave oven. And yet, there have been a few intriguing moments in SETI history. The most famous is the WOW signal, detected in 1977 by Jerry Emmon using Ohio State University's Big Ear radio telescope. It was a 72-second burst of radio energy near the 1,420 MHz hydrogen line, strong, unexpected, and eerily unexplained. Emmons circled it on the data printout and wrote, "Wow," in the margin, hence the name. Despite repeated efforts, the signal was never detected again, and its origin remains mysterious. Was it aliens? A natural anomaly? A freak Earth-based interference? We don't know, but it remains one of SETI's biggest head-scratchers. Today, SETI continues to evolve, taking advantage of machine learning, cloud computing, and crowdsourcing. Projects like SETI at Home, though now in hibernation, allowed millions of volunteers to donate their computer power to analyze signals from space. Think of it as cosmic data crunching powered by idle office PCs and passionate nerds everywhere. One of SETI's ongoing debates is active versus passive search. Most efforts are passive. We listen but don't broadcast. But some scientists, like the late Stephen Hawking, warned against active attempts to send messages into space. The fear is simple. What if the aliens aren't friendly? Broadcasting our location is a bit like screaming your address into a dark forest and hoping whoever hears it doesn't like fire. Still, others argue that any civilization capable of reaching us could already detect Earth's radio leakage, from TV broadcasts to radar pulses. If they're out there and paying attention, they've probably already picked up our signature. In that case, sending a deliberate message isn't a bold risk, it's just good manners. So what has SETI found so far? Absolutely nothing conclusive. Not one confirmed alien broadcast. Not a single verifiable hello. And yet, far from being a failure, this lack of evidence is itself scientifically valuable. It narrows the search, informs our models, and helps refine our assumptions. It tells us something about where aliens aren't, or at least where they're not broadcasting. More importantly, it reinforces the idea that science isn't about immediate answers. It's about asking the right questions over and over with better tools, sharper minds, and just enough optimism to keep listening. Because the truth is, if we ever do hear a signal, even a faint one, it would be the most profound discovery in human history. It would mean we are not alone, that intelligence has flowered elsewhere in the universe, and suddenly, the silence would become a conversation. Until then, the radio telescopes keep turning, the signals keep coming, and somewhere in the cosmic static, maybe, just maybe, someone's out there wondering why we haven't called yet. While the search for extraterrestrial intelligence has historically revolved around radio signals, because, well, it made sense in the 20th century, a growing number of scientists are starting to ask, what if we're using the cosmic equivalent of a rotary phone? In a universe that's potentially billions of years more advanced than we are, it's possible that civilizations aren't bothering with radio waves anymore, and they've moved on to faster, subtler, or more efficient ways of communicating. So let's explore the more exotic and scientifically plausible alternatives. In case the aliens are texting each other with neutrinos and we're stuck still waiting for a busy signal. Lasers are a favorite in modern SETI. They're coherent, focused, and can travel vast distances without dispersing, unlike radio waves that spread out and lose intensity over time. In fact, some lasers we can build right now on Earth could outshine the sun, briefly and in very specific wavelengths, if seen from far enough away. So, if aliens want to grab attention without wasting energy, a directed laser pulse might be their version of a high. This is the basis for optical SETI, where scientists scan for ultra-brief pulses of laser light, just nanoseconds long, that stand out from the natural starlight. If you detect a light pulse that's short and that powerful, it's either a deliberate signal or someone out there just played the most extreme cosmic laser tag. These optical searches are active in several observatories now, including Harvard's SETI program and the Laser SETI project, which is designed to monitor the entire night sky for such pulses. It's a massive effort to spot the equivalent of an alien's high-beam headlights blinking across the void. Next up in our parade of exotic messengers, neutrinos. These nearly massless, chargeless particles barely interact with matter. They can pass through a planet, heck, even through a star, like it's not even there. Convenient if you want to send a message across the galaxy without it getting stopped by dust clouds, solar flares, or bureaucratic red tape. The downside: neutrinos are extremely difficult to detect. You need massive underground detectors like IceCube in Antarctica, which uses a cubic kilometer of ice embedded with sensors to catch the rare occasion when a neutrino collides with something. Sending neutrino signals is theoretically possible, but would require a staggering amount of energy or extremely advanced technology. If aliens are using neutrinos, it's no wonder we haven't picked up the phone yet. We've basically been using cups and string. Ah yes, quantum entanglement. Einstein's spooky action at a distance. In this mind-bending scenario, two particles become linked such that measuring one instantly determines the state of the other, no matter how far apart they are. Sounds like magic, right? Could aliens use this to send information faster than light? Sadly, no. As far as we know, quantum entanglement can't be used to transmit information, just correlations. But the idea keeps popping up in speculative tech and theoretical physics. If a civilization figured out how to manipulate entanglement in ways we don't yet understand, it might allow instantaneous communication across interstellar distances. That said, this sits firmly in the category of cool to think about, but don't hold your breath. Our current physics says no, but then again, our current physics also took a while to accept black holes. Gravitational waves are ripples in space-time caused by massive objects like colliding black holes. LIGO and Virgo have made headlines for detecting them in recent years, and they open an entirely new realm of observation. Could aliens use gravitational waves to communicate? It would be incredibly difficult to generate them on purpose. You'd need something like controlled black hole mergers, which is a sentence that should make your eyebrows rise. But if a civilization has mastered control over gravity, then sure, they might send messages by subtly rippling the fabric of reality itself. That would be impressive and terrifying. We're only beginning to observe gravitational waves ourselves, so if aliens are talking that way, we may just now be joining the right channel. And we're showing up to the conversation like the guy who forgot to unmute. Some SETI researchers suggest that we might detect communication not through waves at all, but through megastructures, massive artificial constructions that manipulate starlight in ways that are hard to explain naturally. A famous and wildly controversial example is KIC 846-2852, also known as Tabby's star. Astronomers noticed strange, irregular dips in its brightness that didn't match anything we'd expect from natural causes like planets or dust. Naturally, someone suggested, maybe it's an alien megastructure like a Dyson sphere? A Dyson sphere is a hypothetical construction, a swarm of satellites or a shell around a star designed to capture most of its energy output. The idea dates back to physicist Freeman Dyson in the 1960s. A civilization capable of building one would be firmly in Type 2 on the Kardashev scale, able to harness the energy of an entire star. If we observed such a structure, even indirectly, it would be a massive hint that someone out there has moved way beyond fossil fuels and solar panels. Of course, Tabby's star turned out to have more plausible natural explanations, probably dust, maybe comets. But the excitement wasn't wasted. It reminded the scientific community that communication may not be deliberate, some civilizations might signal their presence simply by being big, bright, and weird. Beyond megastructures, speculative SETI also considers things like gravitational lensing, bending light using a star or planet's gravity. If aliens use their sun as a lens to magnify signals sent to other stars, it would be a clever, low-energy way to focus interstellar messages. There's also the possibility that advanced civilizations use cloaking technologies or deliberately avoid being noticed. Maybe they're aware of potential threats, or just introverted, and use some form of dark communication that blends into the cosmic microwave background. If so, we're trying to find glowing green letters in a sea of white noise. One recurring theme in all of this is that we're still thinking like humans. We assume aliens want to communicate, that they use waves, that they have something to say. It's entirely possible that they're not even biological anymore, or that their communication is something we wouldn't recognize even if it walked up and poked us in the telescope. They might exchange thoughts via altered gravitational constants, live entirely in simulated environments, or have transcended the need to say anything at all. Maybe we're trying to understand Beethoven by staring at sheet music while deaf. So, are we listening wrong? Maybe. But the beauty of SETI is that we're expanding our toolkit. Radio's still useful, lasers are promising, and gravitational waves and megastructures are on the menu. We're not just asking if aliens are using CB radios anymore. We're asking what language they might be speaking at all, and whether our instruments are even capable of hearing it. The universe might be speaking. We just have to figure out how to listen properly. So far, we've been gazing at the cosmos, listening for signals, and entertaining ourselves with theories about lasers, megastructures, and spooky action at a distance. But if we really want to find extraterrestrial life, especially the microbial kind, we need to do the old-fashioned scientific thing. Go there, poke around, and see what's under the rock. That's where astrobiology and space missions come in. Astrobiology is the interdisciplinary science that investigates the origin, evolution, distribution, and future of life in the universe, which is basically a fancy way of saying it's the science that asks, is anyone else out there? And did they leave any goo behind? This field brings together microbiology, planetary science, chemistry, geology, and astronomy. It's the ultimate scientific mashup, all focused on understanding how life could exist beyond Earth, what it might look like, and how we might recognize it. In other words, it's the science of alien hunting, but with pipettes and spectrometers instead of binoculars and tinfoil hats. So, where have we looked so far? Let's walk through humanity's current and upcoming astrobiological detective work. If the solar system had a suspicious neighbor, it's Mars. It's dry, it's cold, and it has an atmosphere so thin you could cough right through it. But once upon a time, it may have been wet, warm, and life-friendly. NASA has been obsessed with Mars for decades, and for good reason. Evidence of ancient riverbeds, sedimentary rocks, and mineral deposits that form in the presence of water suggests that Mars was once habitable, at least for microbes. Enter Curiosity, the car-sized rover that landed in 2012. It's still exploring Gale Crater and has found all the building blocks of life. Carbon compounds, sulfur, nitrogen, oxygen, phosphorus, the usual suspects. But no actual Martians yet. Not even a bacterium waving a little red flag. Then came Perseverance, which landed in 2021 in Jezero Crater, a site thought to be an ancient river delta. This rover is equipped with the most advanced astrobiology lab ever sent to another planet, including instruments to detect organic molecules and biosignatures. But Perseverance isn't just there to sniff rocks. It's collecting samples that will eventually, hopefully, be brought back to Earth by a future mission. This will be the first time we attempt to analyze Martian soil in a real lab, not just through robot selfies and remote spectrometry. And let's not forget Ingenuity, the tiny helicopter that hitched a ride with Perseverance and casually made the first powered flight on another planet, just to show off. While it wasn't looking for life, it demonstrated our ability to scout the surface from above, a game changer for future missions. If Mars is the dry hope, the moons of Jupiter and Saturn are the wet dream of astrobiology. Literally. Let's start with Europa, one of Jupiter's largest moons. It's covered in a thick shell of ice, but underneath that, a global saltwater ocean, possibly twice the volume of all Earth's oceans combined. This ocean is kept warm by tidal flexing, a gravitational massage from Jupiter that generates internal heat. Scientists believe Europa's ocean could contain hydrothermal vents similar to those on Earth's seafloor, where life thrives without sunlight. NASA's upcoming Europa Clipper mission, launching in the mid-2020s, will orbit Jupiter and perform dozens of flybys of Europa. It'll analyze the moon's ice crust, subsurface ocean, and strange reddish streaks on its surface that may hint at organic compounds. It won't drill through the ice yet, but it's setting the stage. Then there's Enceladus, a tiny moon of Saturn that blew scientists' minds when the Cassini spacecraft discovered plumes of water vapor and organic molecules shooting out of its south pole. That's right, it's spewing possible life ingredients into space like it's auditioning for the alien Olympics. Cassini actually flew through those plumes and analyzed their contents: water, salts, methane, and complex organics. So now we know that Enceladus has a subsurface ocean, heat, and organic material. That's a trifecta of potential habitability. A future mission, like the proposed Enceladus Orbolander, could land, sample those plumes directly, and maybe, just maybe, find signs of life. Staying with Saturn, let's talk about Titan, the only moon in the solar system with a thick atmosphere. And not just any atmosphere, it's rich in nitrogen and methane. Titan has liquid lakes and rivers on its surface, but they are made of hydrocarbons, not water. In other words, it's Earth's evil twin in a lab coat. Titan is fascinating because its surface chemistry might resemble early Earth's before life took over. NASA's upcoming Dragonfly mission, launching in the 2030s, will land a flying drone on Titan to explore its terrain and analyze complex organic chemistry. Titan might not have life as we know it, but it could have the precursors to life, or some very weird alien chemistry that challenges our assumptions. Once thought completely inhospitable, Venus has crept back into astrobiology discussions. Despite being a volcanic pressure cooker, a recent and controversial claim of phosphine in its upper atmosphere sparked speculation. Phosphine is associated with biological processes on Earth, and its detection, if confirmed, could point to microbial life in Venus's cloud layers, where temperatures and pressures are less extreme. This has led to a renewed push for Venus missions. NASA's Veritas and Da Vinci Plus, along with ESA's Envision, are all set to explore Venus in the coming decade, mainly to study its geology and atmosphere, but with an eye on astrobiological implications. Let's not forget our more distant hopes. While we can't send spacecraft to exoplanets yet, missions like Kepler, TESS, and now the James Webb Space Telescope, JWST, are helping us identify worlds that might be habitable. JWST, in particular, can analyze exoplanet atmospheres for biosignatures, gases like oxygen, methane, and carbon dioxide in ratios that suggest life. It's our best tool yet for remote alien forensics. If we detect something weird, like high oxygen and methane together on an Earth-like planet orbiting in the habitable zone, that would be a major red flag or green flag depending on your optimism for life. For all our missions, tools, and scientific ambition, we haven't found conclusive evidence of life. Not on Mars, not in Europa's ocean, not in Titan's tar pools. But here's the thing. Absence of evidence is not evidence of absence. We've barely scratched the surface, literally. Most of our probes have only gone skin deep. We need more missions, better tech, and probably a bit more patience. Life, especially microbial life, might be hiding under ice, deep underground, or floating in clouds. It may not want to be found easily, but astrobiology isn't about instant gratification. It's about building the long game, layer by layer, mission by mission. And who knows? The first proof of life beyond Earth might come from a chunk of ice on a distant moon, a puff of gas in a Venusian cloud, or a strange signal in a Martian rock. All we have to do is keep going, keep looking, and, perhaps most importantly, keep drilling. Despite our increasingly sophisticated instruments, detailed missions, and maturing scientific theories, there remains a category of phenomena that stubbornly refuses to yield simple explanations, what we might call observed anomalies. These are the tantalizing, sometimes frustrating data points that don't quite fit. They're the puzzle pieces that seem to belong to a different puzzle entirely. And while they rarely offer conclusive evidence of extraterrestrial life, they often dance around the edges of possibility, tempting the imagination and testing the rigor of science. Let's be clear, anomalies are not proof. They are deviations, patterns, or events that either remain unexplained or resist convenient categorization. But in science, anomalies are often the first sign that we're on the brink of something new, provided we investigate them properly and don't fall headfirst into conspiracy rabbit holes. One of the most famous examples in the search for extraterrestrial intelligence is the so-called WOW signal, detected in 1977 by the Big Ear radio telescope at Ohio State University. This 72-second burst of radio energy came from the constellation Sagittarius and had all the characteristics of a potential artificial origin: narrow bandwidth, signal strength, and duration. It stood out so dramatically that the astronomer who discovered it literally wrote, "Wow," in the margin of the printout. But here's the twist: it never repeated. Not once. Despite decades of follow-up efforts, the signal has never reappeared, and no source has been identified. Was it a glitch? A cosmic fluke? A passing satellite? Or an alien civilization transmitting once, then ghosting us forever? As you might imagine, the scientific consensus is cautious, interesting, but insufficient. In short, WOW became more of a hum. This is far from the only unexplained signal or anomaly to raise eyebrows. Over the years, radio telescopes around the world have occasionally picked up transient signals, short bursts, or narrow bandwidth emissions that mimic what we might expect from artificial sources. Some have been quickly debunked. One particularly notable example turned out to be a malfunctioning microwave oven in the observatory's kitchen, truly a moment of culinary sabotage. Others remain in the unexplained but not compelling category, the liminal space where most scientific anomalies live until further evidence tips the scale. More recently, attention has turned to the renewed interest in unidentified aerial phenomena, UAPs, what the rest of the world still calls UFOs. In an unexpected twist of history, the U.S. government, NASA, and the Pentagon have publicly acknowledged the existence of aerial encounters that defy conventional explanations. In 2020, the Pentagon even established the All-Domain Anomaly Resolution Office, ARO, to investigate these reports, particularly those from military personnel. Some of the footage, grainy black and white videos from fighter jets, shows objects accelerating, changing direction, or hovering in ways that defy known aerodynamics. It all feels a little too much like the opening scene of a science fiction movie. But the language used by officials remains incredibly careful. These are unidentified phenomena, not confirmed alien spacecraft. Most scientists remain skeptical, if not outright dismissive, pointing out that the lack of clear data, the unreliability of eyewitness accounts, and the high probability of misidentification, drones, weather balloons, sensor glitches, make it far more likely that we're seeing earthly tech or natural phenomena. Still, the fact that UAPs are now being studied seriously by scientists, not just enthusiasts, is a marked shift in tone from the ridicule of previous decades. And then there are the astronomical oddities. One of the more fascinating examples is Tabby's star, KIC 846-2852, a star whose brightness dipped in highly irregular and significant ways, up to 22%, with no clear periodicity. When first discovered, some scientists seriously considered the possibility of a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harness stellar energy, as a potential explanation. Again, caution prevailed. Follow-up studies suggested dust, cometary fragments, or some other natural phenomenon as more likely explanations. But the key here isn't that we proved aliens didn't cause the dimming. It's that such a possibility was discussed in peer-reviewed papers and taken seriously, an indication that science, while cautious, is willing to entertain the extraordinary when the data nudges in that direction. Another subtle but persistent category of anomalies comes from the atmospheres of exoplanets. As we've developed the ability to study these distant worlds through transit spectroscopy, essentially analyzing the starlight filtered through an exoplanet's atmosphere, we've occasionally detected unusual combinations of gases. High levels of methane alongside oxygen, for example, could be a potential biosignature, since such a mix is hard to sustain without continuous biological processes. So far, no planet has displayed a smoking gun, a clear, reproducible biosignature, but the instruments are improving and the signals are growing more tantalizing. What's important in all these cases is not the anomaly itself, but the response to it. Science thrives on questions, but only when those questions are investigated methodically. Jumping from, "I don't know what that is," to "it must be aliens," is intellectually lazy. The scientific method demands skepticism, repeatability, and evidence. A blurry photo or a one-time signal doesn't cut it, no matter how many Reddit threads insist otherwise. That said, anomalies serve an important role. They expand the perimeter of our understanding. They reveal the limitations of our current models. They invite new hypotheses, better instruments, and fresh perspectives. Some anomalies eventually become paradigms. Think of how the unexplained precession of Mercury's orbit led to general relativity. Others fade into obscurity once better data arrives. And yet, we're human. We're story-driven, meaning-seeking creatures. The unexplained compels us, and rightly so. That edge of the map, uncertainty, has historically been where some of our greatest discoveries have emerged. So while the signal, Tabby's star, and the UAP footage don't prove anything definitive about alien life, they serve a critical purpose. They keep us looking. They remind us that not everything fits neatly into our current understanding, that the universe still has secrets, and that maybe, just maybe, one of these anomalies will one day be the first crack in the door between us and someone or something else. And wouldn't that be something? If extraterrestrial life has yet to knock on our front door, or, at the very least, send a courteous radio ping, it certainly hasn't stopped us from rolling out the welcome mat. Aliens, in all their imaginative glory, have thoroughly infiltrated our culture, literature, cinema, philosophy, and even, quite ironically, scientific inquiry. Despite a distinct lack of confirmed encounters, the influence of aliens on human thought has been colossal. They've shaped dreams, fears, futures, and funding proposals. In short, aliens have colonized our imaginations, if not our planet. To understand this influence, we need to look at two parallel threads: how aliens have evolved as a cultural construct, and how that construct has in turn influenced real scientific thought, sometimes in productive ways, sometimes in ways that have scientists burying their heads in their lab coats. Let's start with the arts. From ancient myths of sky gods and chariots of fire to modern science fiction, humanity has long been fascinated by beings from beyond. Many early interpretations of celestial visitors were wrapped in religious or mystical imagery. Ancient civilizations, without telescopes or astrophysics, interpreted what they saw in the skies through a mythological lens. Deities, demons, and cosmic battles made sense in a world without spectrometry. But as our understanding of the cosmos expanded, so did the sophistication of our imagined visitors. Enter science fiction, the genre that arguably gave aliens their modern form. With authors like H.G. Wells, Arthur C. Clarke, Stanislav Lem, and later Ursula K. Le Guin and Octavia Butler, aliens became tools for exploring not just science, but sociology, ethics, colonialism, and the human condition. The War of the Worlds, 1898, terrified readers with a vision of technologically superior invaders. Childhood's End offered benevolent overlords who quietly ushered humanity into transcendence. Whether aliens arrived to destroy, enlighten, enslave, or simply observe, they became mirrors, reflecting our hopes, fears, and deepest uncertainties about our place in the universe. Hollywood, of course, took these narratives and turned them into visual spectacles, and occasionally into pure kitsch. From the rubbery gray heads of 1950s B-movies to the sleek horrors of Ridley Scott's Alien, from Spielberg's friendly E.T. to the multi-layered linguistics in Arrival, aliens have become as versatile in film as they are theoretically diverse in space. Some teach us to love, others teach us to scream, and still others, apparently, just want to probe things. We don't talk about those. What's fascinating is how these cultural depictions have fed back into the scientific world. You might think that scientists would roll their eyes at the portrayal of aliens in pop culture, and to be fair, many do. But others recognize that these stories, no matter how fantastical, serve a vital role. They fuel curiosity. Carl Sagan himself, arguably the most respected science communicator of the 20th century, understood this. His novel Contact was both scientifically grounded and deeply imaginative, merging hard data with the soft edges of human belief. The cultural obsession with aliens has also had very real consequences for scientific funding and public interest. Programs like SETI, Search for Extraterrestrial Intelligence, owe part of their longevity to the public's enduring interest in Are We Alone? The fascination with alien life has driven telescope construction, space missions, and advanced theoretical models. Scientists may be searching for microbes, not flying saucers, but the cultural backdrop of alien fascination helps keep these endeavors relevant and funded. At the same time, we can't ignore the dark side of this cultural influence: pseudoscience and conspiracy theories. For every scientifically grounded discussion of extremophile bacteria on Europa, there's a late-night TV special about Area 51, alien abductions, and government cover-ups. While some of these tales are harmless fun, others have real consequences. The spread of misinformation and the elevation of anecdote over data can muddy public understanding of science. In the worst cases, it can undermine trust in institutions and research. The irony is that the same cultural fascination that inspires genuine scientific inquiry also fuels baseless speculation. Scientists working in astrobiology must constantly navigate this minefield. On one hand, invoking the possibility of alien life draws attention and resources. On the other, too much speculation can harm credibility. It's a delicate balance between inspiring wonder and maintaining rigor. And yet, we must give credit where it's due. Cultural narratives about aliens have broadened the scope of inquiry. They've pushed science to ask not just what could life elsewhere look like, but how would we even recognize it? Would it be microbial or machine? Would we know intelligence if we saw it? These are questions that go beyond lab experiments. They require philosophy, anthropology, linguistics, and yes, a touch of imagination. There's even a growing field called exocultural studies, a blend of anthropology and astrobiology that attempts to imagine what alien societies might value, how they might communicate, and how we might establish a dialogue. Granted, it's speculative, but it's also a recognition that if intelligent life exists elsewhere, we'll need more than radio telescopes to understand it. We'll need empathy, and perhaps subtitles. It's also worth noting that in imagining alien civilizations, we're often talking about ourselves, projecting human traits onto hypothetical beings. Some are conquerors, some are saviors, some are scientists, and some are gods. We imagine aliens as everything we fear and everything we aspire to be. They become a lens through which we explore our own evolution, ethics, and future. In that sense, the cultural impact of aliens has done something remarkable. It has turned a complete absence of evidence into one of the most powerful engines of speculation and innovation in human history. Even without proof, the idea of aliens has influenced everything from AI ethics to space policy. They haunt our literature, guide our research, populate our entertainment, and drive billionaires to build rockets. Not bad for a concept with zero confirmed sightings. And who knows, maybe someday, long after we've exhausted every telescope and drilled through every icy moon, we'll find something, some signal, some spore, some techno-gadgetry in orbit around a distant star, and we'll look back and realize the fiction helped us imagine the truth. Until then, we write, we dream, and we probe, scientifically, of course. Let's pretend, just for a moment, that it happens. A message is received, unambiguously artificial, from somewhere light years away. Or perhaps a probe is found drifting silently through our solar system, loaded with data in an alien script. Or maybe the contact is even more dramatic. A craft descends, hovering silently above Earth as the world collectively forgets how to breathe. The point is, contact, the thing scientists, philosophers, theologians, and late-night radio hosts have speculated about for centuries, finally occurs. Now what? If science fiction has taught us anything, besides never splitting up the group, it's that first contact is never just about physics and engineering. It's about ethics, identity, morality, meaning. It shakes the foundation of what we know or thought we knew about ourselves. The moment we confirm we are not alone in the universe, the game changes. For science, yes, but also for philosophy, religion, law, and global politics. Let's start with the big question. Should we even try to make contact? There's a surprisingly fierce debate in the scientific community about this. Projects like METI, Messaging Extraterrestrial Intelligence, have taken it upon themselves to send signals, mathematical, musical, even DNA-based, into the cosmos. The rationale? If aliens are out there, and we're listening, shouldn't we also be saying something? Others vehemently disagree. People like Stephen Hawking have warned that actively announcing our presence could be a spectacularly bad idea. akin to ringing the dinner bell in a jungle and hoping that whatever hears you is in a good mood. The logic follows historical precedent. Whenever a technologically superior civilization has encountered a less advanced one here on Earth, the results haven't exactly been great for the latter. Exhibit A, colonialism. Exhibit B, basically every time Europeans discovered anything. So, ethically, the question becomes, do we have the right to speak for Earth? Who gets to craft the message? Scientists? Politicians? Influencers with high engagement rates? And what would that message say? A simple hello might suffice, or we could attempt to summarize thousands of years of human civilization in a compressed binary format and hope we don't accidentally offend anyone by putting pineapple on our cultural pizza. Then there's the issue of interpretation. Suppose we receive a message, a real, intelligent, structured message. What moral responsibilities do we have in deciphering it? Should the information be shared globally or quarantined for analysis? Is it ethical to keep it from the public or unethical to expose humanity to a message we don't fully understand? There are also questions of consent and risk. By responding, we may reveal more than we intend, not just our presence, but our location, our biology, even our weaknesses. This raises not only practical risks, but philosophical ones. In choosing to respond, we are essentially speaking for all of humanity. That's a big burden for any group to carry. The philosophical impact of contact might be even more profound than the scientific one. For centuries, many belief systems have operated with the implicit assumption that humans are the center, or at least the focus, of the universe. The discovery of intelligent extraterrestrial life would force a reckoning. Some religious doctrines might adapt gracefully, interpreting aliens as part of a grander divine plan. Others might resist or fracture. Some people would embrace the cosmic community. Others might deny the reality altogether. Humans, as history shows, are not uniformly rational in the face of paradigm shifts. The question of personhood is also central. If we do meet intelligent life, how do we define its moral status? Are they equals? Do they have rights? Would it be ethical to study them, interact with them, or intervene in their world? These are questions we've struggled with even among our own species. The idea of applying them to beings that may think, communicate, or exist in ways utterly alien to us adds an entirely new level of complexity. Moreover, contact would force us to confront our cosmic identity. What does it mean to be human if we are not unique? How do we define intelligence, consciousness, or even life when faced with something so fundamentally different? Our philosophies of mind, ethics, and even aesthetics could all be thrown into question. It's not unlike suddenly discovering you're not an only child. You have siblings out there, and now you have to figure out the family dynamic. Some thinkers speculate that contact, especially with a vastly older civilization, could trigger what's been called the philosophical singularity, a moment in which our collective worldview is upended so completely that nothing afterward is quite the same. That's not just hyperbole. The knowledge of another, advanced, enduring intelligence could reshape our values, our priorities, and our existential goals. For some, this might be inspiring, a challenge to rise to the occasion. For others, it might be paralyzing, a blow to the illusion of human supremacy. Interestingly, many philosophical models also explore the idea of non-interference, echoing the so-called prime directive from Star Trek. If we discover a less advanced civilization, are we morally obligated to leave them alone? To allow them to develop on their own terms? Could we resist the urge to intervene, even for noble reasons? This isn't just idle speculation. It mirrors ethical debates we already face here on Earth regarding indigenous cultures, animal rights, and environmental intervention. Ultimately, the ethical and philosophical aspects of alien contact boil down to one profound question. What kind of species do we want to be when we are no longer alone? Will we be ambassadors of peace or projections of fear? Will we welcome the unknown with curiosity or recoil with suspicion? Will we look outward with the same moral courage we expect in ourselves? Or will we project our old biases and conflicts onto the stars? Preparing for alien contact isn't just a matter of science or policy. It's a moral rehearsal, a test of empathy, imagination, and restraint. And perhaps most critically, it's a reflection of our readiness, not just to encounter the other, but to understand ourselves in the process. Because contact, should it happen, won't just answer the question, are we alone? It will ask a much deeper one. Who are we, really, when someone is finally watching? And so, after traversing the scientific, philosophical, cultural, and speculative landscape of extraterrestrial life, we arrive at the end, or rather, the edge of the known. A place where questions outnumber answers, and possibilities outshine certainties. The question, do aliens exist, may sound like the premise of a late-night sci-fi rerun, but as we've seen, it's a legitimate scientific inquiry, one that cuts across disciplines, challenges our assumptions, and pushes the boundaries of human understanding. And while the answer is still elusive, the journey to find it has already transformed how we think, search, and dream. Let's take stock of where we are. Astrobiology, once a fringe field whispered about in university hallways, is now a thriving discipline supported by major institutions like NASA, the European Space Agency, and a growing number of universities worldwide. We're sending spacecraft to icy moons, designing next-generation telescopes to sniff out distant exoplanet atmospheres, and scanning the cosmos for any whisper of an intelligent signal. Our tools are improving, our theories are sharpening, and perhaps most importantly, our curiosity shows no sign of waning. One of the key insights of this journey is just how resilient the idea of alien life has been. Not because we've seen definitive proof of Martians with laser guns, thankfully, but because the science keeps suggesting, again and again, that the conditions for life might not be rare after all. We've learned that life on Earth is stunningly adaptable, thriving in acidic lakes, under kilometers of rock, and near hydrothermal vents that would cook most organisms to death. We've discovered thousands of exoplanets, many in their stars' habitable zones, some with atmospheres hinting at chemical oddities. All of this adds weight to what was once only speculation, that life may not be a cosmic fluke, but a cosmic tendency. Of course, that's still a hypothesis. The great irony of the search for aliens is that it's largely a hunt for ourselves, for patterns and chemistry and structures that mirror the only model of life we know, Earth life. We don't yet know if life can exist in forms completely unfamiliar to us, silicon-based, plasma-based, or something stranger still. Our tools are, by necessity, biased toward the known. It's the intellectual equivalent of using a flashlight in the dark. You see only what the beam touches. And yet, even that narrow beam is revealing more than we once dreamed possible. Looking forward, the next few decades may finally begin to answer the long-standing question. Missions like Europa Clipper and Dragonfly will explore moons that may host subsurface oceans. The James Webb Space Telescope, and its eventual successors, are beginning to analyze exoplanet atmospheres with enough detail to detect potential biosignatures: methane, oxygen, ozone, maybe even industrial pollutants, because nothing says intelligent life like dirty air. SETI continues to expand its capabilities, not only listening for radio waves, but also scanning for laser pulses, anomalous heat signatures, and even technosignatures. indications of advanced engineering, like Dyson spheres or artificially regular planetary orbits. There's also a growing recognition that the discovery of extraterrestrial life may not come as a blaring trumpet fanfare, but as a whisper in the data, a strange reading here, a blip there, a pattern that refuses to fit. In other words, the first contact might not be a moment of cinematic revelation, but of painstaking, skeptical, rigorous analysis. It might even be retroactive, realizing, years later, that a signal we dismissed was something more. But even if we find nothing, if we look out into the cosmos for another 1,000 years and hear only silence, that itself is a result. The so-called Fermi paradox, which asks why we haven't found any signs of intelligent life despite the high probability of its existence, may hint at deeper truths about the nature of civilizations, technological survival, or even the limits of our perception. Silence can be as instructive as signal. It tells us something about our place, our expectations, our hopes, and perhaps, most crucially, the search forces us to confront how we define life, intelligence, and meaning. It makes us ask who we are, biologically, ethically, culturally, in a universe that may or may not be listening. In a way, this grand question, are we alone, is the ultimate scientific koan. It can't be answered easily, and any potential answer comes with its own cascade of new questions. If we are alone, why? Is life that rare? Are we the first or the last? If we're not alone, where's everyone? What are they waiting for? Are they so different from us that we wouldn't even recognize their message? But here's the beautiful thing. Regardless of the answer, the pursuit itself elevates us. It pushes us to explore, to understand, to imagine. It unites disciplines, astronomy, biology, philosophy, engineering, and even art. It invites humility and wonder in equal measure. In short, the search for extraterrestrial life may be the most human thing we do. And so we listen. We search the skies, the soils of distant moons, the spectra of alien atmospheres. We argue and speculate and build ever better machines. We imagine worlds and beings and languages and philosophies. And in doing so, we learn more not just about the cosmos, but about ourselves. Because whether or not aliens exist, one truth remains unshakable. We want to know. We need to know. That drive, to look up and wonder, is not a flaw. It's the finest part of us. And if, one day, something out there answers back, well, let's just hope they've seen our best work, and not just the YouTube comment section. Good night.